Hello? Hello? Is anybody out there? Can you hear me? Can you hear me? Can you hear me? Excellent. Excellent. Glad to have you with me. Okay, so we will be starting in just a little bit. I'm going to give everybody an opportunity to get into the chat room. Be thinking of any questions you've got for me, and I'll be right with you. How we doing, everybody? How we doing, everybody? Is everybody thinking of some questions to ask me to help you with your quiz tomorrow? This is an interactive thing that we got going on. Am I correct in assuming that that DI1 Logan is Logan? Is that for real? It's nice when I can discern the names of whoever it is. But glad to have you. Y'all been thinking up some questions for me? Excellent. Okay, so let's give this another 1 or 2 minutes and then we'll be ready to go. But feel free to start asking your questions now so I can start preparing my answers. Okay, the more questions I have, the better this whole thing goes for everybody. Hi, how we doing? We've got 8 people watching. Welcome to Fortnite Physics. This is my Tuesday office hours, my live stream for a quiz that we are having in our class tomorrow over constant velocity and graphing motion. Okay, if you are new, we'll be starting in just a little bit. Please hit that follow button and check in every Monday and Thursday for my office hours during Black Ops 4 and Fortnite. I've already gotten a couple of ideas of stuff to get going. Let's give it just 30 more seconds and we'll get started. Does everybody like my overlay that I've got going for this this format that we've got going here? Excellent. Okay, well, let's go ahead and get started. All right. So, how are we doing, everybody? So, you guys can see. Oh, hi, Frank. You're D1 Logan. Well, nice to see you. All right. So, let's see what we've got. Okay. You can see I've got my thing. I'll try my best to write big, and I've got all my stuff going. My chat's a little strange, but oh well. All right. So let's go ahead and get started. We're going to graph some motion. Okay. Now, if we start off with a graph that looks like the following. And this is a position versus time graph. What can we say about the motion of this object? Okay, we are interested in figuring out what is happening to this object and we're going to see everything we can figure out about it, okay? So we can tell that it starts somewhere far from the, well, somewhere from the origin in the positive direction. We have the positive direction up here. So we are starting somewhere from the origin, and we are moving away from the origin more positively as time progresses. Now we move with a straight line, so this is a constant velocity. Now, who out there can remember for me what happens here with a horizontal line? Who can tell me that? Okay, well, either way, anyway, so that means, the horizontal line means that we are stopped. Position's unchanging, nothing is moving, and there we go, okay? So we are paused through this part of the motion. Now, during this piece right here, we are moving in the negative direction towards the origin, and we're headed back towards our origin. See, our position is becoming less and less positive. And then from here, we are stopped again. But now let's go ahead and add in some numbers, okay? So let's add some numbers for time and for displacement. So let's say this is 2 and this is 4. Exactly, constant speed. Good job. Good job, Frank. Okay, so we have this going right here from 2 to 4. And let's say this is from 0 to 4 seconds, and that this is from 4 to 8 seconds. 8 seconds, and that this is 10 seconds. I need a new marker. And that this is 12 seconds. Okay, excellent, excellent. Now we can figure out just how far we have traveled in distance and displacement. Okay, so in distance, everything, all of the motion is recorded. Okay, so anything going away, anything coming back, everything is recorded in our distance. All right, so we can see that we move from 2 to 4. Now, how far is it from 2 to 4? It is 2, right? From 2 to 4, there's 2 units of distance. So we've moved from 2 to 4. So starting our calculation, we can say 2, because from 2 to 4, that's 2. We're stopped through this portion right here, and then we travel backwards 2, from 4 back to 2. And again, since we count everything in our distance, that's another 2. And we are stopped from here to here. So that's it. Just 2 plus 2 equals 4. Okay? That's our distance for what is shown in this activity. Now, if we try to calculate our displacement instead, what we're going to do is we're going to count this from 2 to 4, but that's in the positive direction, right? Because we're going further away from our origin. So that's a 2. But even though we're going from 4 to 2, and it's still the same amount of distance, it is a different amount of displacement because it's in the negative direction. So instead of plus 2, it'll be minus 2, and our total displacement for this is 0. Okay? Excellent, excellent. 2 units. Fantastic. Everybody be thinking of good questions, because when I'm finished with this, we're going to need something else to talk about. Okay? So now, let's see if we can't figure out our velocities for this period of time, from 2 to 4 over 4 seconds. Can we do number 5? I'm lost. Okay. I need you to type in number 5 for me as best you can. I forgot to bring that material home, but we can answer any other questions. Actually, you know what? I can pull that up. Okay, so pull up Okay. I can get physics K, classwork number 5. Resources, velocity problems number 5. Boom, there we go. Okay, I'll get that one in just a second. I'll be right back after that. Okay, so we're trying to figure out our velocity, and we already said that our velocity on a position versus time graph is the slope. Okay, so we're looking for the slope of these lines. That's what we're looking for. Okay, so our v from here, we calculated rise over run, y2 minus y1 over x2 minus x1. Yeah. Well, our y2 is going to be this 4 way up here, as well as our x2 is 4 seconds. Okay. So let's go ahead and write that in. 4 and 2, or no, 4 and 4. 4 and 4, because this is our y2, that's our x2, minus our y1, which is this 2 right here, minus our x1, which is 0. Okay, so 4 minus 2 is 2 over 4 equals 0.5 meters per second. Uh-oh, running off the edge there. 0.5 meters per second. Okay. Now let's do the same thing, but for section C. Okay, we'll do the same thing for section C. So VC. All right. Same deal, but in this case, our y2 is this 2 right here. So 2. And our x2 is 10 divided by 10, minus our y1 is way up here, so that one was 4, and our x1 is 8. Okay, so 2 minus 4 is negative 2, divided by 10 minus 8, or 2, and we have negative 1 meters per second. So even though they were traveling in similar fashions from the same amount of distance, they had very different velocities because they were headed in a different direction and their slopes were different over that period of time. Okay? Does anybody have any questions before I move on from this activity? Okay. Well, cool. So take a picture, screenshot, whatever, and we'll move on. I want to do one more graphing question before I do number 5, but don't worry, Maddie, I will get to number 5 as soon as I finish that problem. Okay. So everybody got this one? Oh, hey. Thank you for following, Loco Limones, Crazy Lemons. Welcome to my classroom. All right, so let's see. Now I want to take I want to take a position versus time graph and again talk about 4 and let's say 3. I want to take the time to figure out how far it went, what its displacement is, so d delta x, and then I want to figure out the velocity versus time graph for the same activity, for the same motion. Okay, and I can already tell I'm going to need a negative part to this. Okay, so now we started at 0, and again we'll just assume meters in seconds. I'll just write that. I'll write that over here. X in meters and time in seconds. Excellent. There we go. Okay, so there we go. Now our distance, we can tell that we went from 0 to 4. So again, it's just going to be 4, and then from 4 back to 0. So another 4 or 8. Now who can tell me, or who can already tell what the what the displacement is going to be. It's going to be pretty much the same thing as we did before, where we took 0 to 4, and then again it moves backwards along this activity, so minus 4 and again 0. Right? Now we are going to figure out our velocities and then graph them. Okay? So from here to here we're going to do the same thing. Our slope of this line, our slope of that line right there, is the velocity from 0 to 3 seconds. So our slope m is just rise over 1 y2 over y1 over x2 minus x1 for both of these things. We just have to identify our y2 and our y2 and our y1. Okay, so let's go ahead and do this math down here. All right. Zoop. Okay, so our m for section A, and then we'll do one for section B. Our m is our y2, which is way up here at 4, minus our y1, which is way down here at 0, and then our x2, which is way over here at 3, minus our x1, which is over there at 0. So we end up with 4 over 3. I know it looks like a 9. 4 over 3. This is, okay, so Maddie, this isn't a direct question off of any of the assignments, but I noticed I didn't do much in the way of graphing motion over the last couple of days, so I wanted to make sure that I hit that first before we moved on from any of this. Okay, so this one is just a general, very valuable question to this whole thing, and as soon as I'm done with this and we graph it all out, I'll do number 5 for you. Okay, we good? Okay. I do want to address briefly the black box in the upper left-hand corner. My webcam didn't arrive yet today. It'll probably arrive in the next couple of minutes. It just didn't arrive quickly enough for this particular stream, so we'll probably have it before the test. Okay. So pardon me, just 1 second. Ooh, there we go. Okay. So we calculated our velocity as 4 over 3 meters per second. And because this line from here to here is straight, we know that it is a constant velocity. Okay? So we can just graph from here to 3 seconds a horizontal line that represents a constant velocity from 0 to 3 seconds at 4/3 meters per second. Okay? And now from here down, you know what? Just to make it more interesting, let's say this is 8 seconds instead of 6. Okay, to make the math a little more interesting. I'm going to erase this little bit down here so that we can do the next one without falling off a frame. Okay, so this doesn't change anything about our displacement or our distance. We still went from 4 back to 0. So that still leaves us with 8 and 0. But we're going to calculate our second slope over here at B, and that gives us our second y, our y2, right down here at 8. So over here at 8. And then our, actually I was wrong. That's 0. Our y2 is 0, minus our y1, which is 4, divided by our x2, which is 8 over here, minus our x1, which is 3. Okay, so we end up with negative 4 over 5. And again, that matches what we expected to see. Okay, we saw that our displacement was headed back towards the origin, and as a result that line had a negative slope, so we expect that we would have a negative velocity. And in this case we got exactly what we expected, a negative 4/5 from 3 to 8 seconds. Okay, so down here at 3 seconds, straight over, and we're going to go ahead and call that 4/5. Okay, so that's all that shows is a constant velocity at 4/3 from 0 to 3 seconds, and then a constant velocity from negative 4/5 from 3 to 8 seconds. Okay? Pretty straightforward, right? And let's see if the math that we can do over here can give us the same distance and displacement numbers that we got in this first one. Y is y2 0. Okay, so Alex, y is y2 0. Okay, so y exists on this axis right here, right, the vertical axis. Now this point right here is our point 2 on when we're calculating our slope for this second bit right here. Now, what is the y value of this point right there? It's along the x-axis, so the y value of this point is 0. So that's why our y2 is 0. Our x2 is way over here at 8, and there we go. That's how we picked our points. So let's figure it out. Now, I told you the way to calculate a distance with a velocity versus time graph was to calculate the area between the line and the, all right, absolutely, Casper Inc. 228. Who is that? I like knowing first names so I can address you more familiarly. But yeah, I can do number 5 and number 7, no problem. All right, and is this the L or the K? The L or the K worksheet, because I've got both. So please identify. Either way, so let's go ahead and calculate our area under the curve, our area between the line and the x-axis. Okay, so each one of these is a rectangle, right? And the area of a rectangle is just base times height. A equals base times height. Now the base of this rectangle is 3. So we're going to multiply 3, and our height is 4/3. And because we don't care about signs or anything, we're just going to go ahead and do the same thing plus this guy over here. So our base is from 3 to 8, or 5, multiplied by 4/5. Okay, and again, distance cannot be negative, so we just strike off the negative. Everything's absolute values. Okay, so 3 times 4/3 is just 3, or just 4, because these 3's cancel out. 5 times 4/5, again, those 5 cancels out, so it's just 4 plus 4, or 8. And now let's do the same thing, but with our displacement. This one above, oh yeah, absolutely. Number 5 on the K worksheet is next up. All right. So right here, this rectangle is 4/3, same as for distance, because it happens to be positive. So 3 times 4/3. Those 3's cancel out. We're left with the 4. But down here, now we take into account this negative. So we have plus 5 times negative 4/5. These 5's cancel out, and we have 4 minus 4 equals 0. So our math agrees. We have our position versus time graph, and we used it to calculate our distance and displacement. Then we used the slopes to graph a velocity versus time graph, and these horizontal lines indicate constant velocity. We used our method of calculating the area between the lines and the x-axis to calculate our distance, which again agreed with what we got over here, and our displacements, which again matched up. So we can be very confident that our math is in fact correct. Everybody take any pictures you need to, and I will move on in about 30 seconds. If you're not one of my students, please stick around and see our discussion about physics. Usually we have a pretty lively discussion going on. My name is Aaron Blades, and I teach physics in Houston, Texas. I like to try to teach through video games. I stream on Mondays and Thursdays, and sometimes in this format as a lecture supplement for my students. So, you know, if you want to get in on the discussion, please let us know. let's move on. Can anybody tell this was a free overlay? Because I feel like I can. It's still pretty cool though. I will continue to update. Alright, so number 5, let me take a look at it real quick. So number 5, okay, hold on one second. Okay, so resources. Alright, I apologize for this delay. Has anybody taken the opportunity to conduct some peer tutoring or finished up some of my tutor tickets or anything like that? It would be quite exciting. Okay, so velocity problems K. Alright, so number 5. Eustace drives 20 kilometers to the east when he realizes he left his wallet at home. He drives 20 kilometers west to his house and takes 5 minutes to find his wallet and then leaves again. Eustace is 40 kilometers east of his house exactly 60 minutes after he left the first time. What is his average velocity? What is his average speed? Okay, so let me make sure I'm still on frame here. Alright, so Eustace drives 20 kilometers east. This is the right one, right? Somebody tell me if I'm doing the wrong one. So 20 kilometers east, then he turns around and drives 20 kilometers west, right? Then next, he continues 40 kilometers from this point over. There we go. And he makes it to this point right here 60 minutes after he began, right? Okay. Now, the part that's tripping you guys up, correct me if I'm wrong, but I'm not, because Mr. Blaze knows everything. What is tripping you guys up is that 5 minutes that he's looking for his wallet. Is that true? Okay. I don't understand anything. Oh my goodness. Okay. That is untrue. I'm certain, Madison. I'm sure you understand more than you gave yourself credit for. But let's go ahead and talk anyway. Okay, so he started here, drove 20 this way, drove 20 back, and then drove 40 over this way. Okay, so that 5 minutes doesn't matter. It even says so right in the problem that he is here 60 minutes after he started. Okay, now that's the important part. That 5 minutes in there is very skillfully doing what it's supposed to do and just confusing you. All right, it's one of those skills that you'll get from repeating lots and lots and lots of these. Is you'll start to recognize which of the pieces of information we've given you are nonsense, or at very least don't apply to anything that you are expected to tell us. Okay, so that 5 minutes means nothing. It means nothing to anybody at all. And let's just move on. Okay, so we started here, drove 20, drove back 20, drove 40, and we arrive here at 60 minutes. Okay, so our two equations, the two that we are relevant to this, are calculating speed and calculating velocity. Okay, so our speed is just our distance divided by our time. Now we don't know our speed, and we do know our time, but we don't know our distance either. So we have two unknowns in this equation. So we need to solve for one or the other so that we can do our math, right? So let's solve for our distance. Now, distance is the accumulation of all of the meters traveled, right? And is this in miles or meters? In kilometers. Okay, kilometers. Okay, so we start off with 20, drives from here to here, 20 km. Then drives back 20, so again, 20 km. 20 plus 20, right? And then drives from here to here, 40 km. 20, 20, 40. Boom. There we go, right? 20 plus 40 is 80 kilometers. Okay? Now, we only have the one unknown left. We don't know our s, but we do know our distance, and we do know our time. All right? So we can just plug in up here. S is equal to 80 kilometers. Keep those in mind. Divided by 60 minutes. Okay? Now, it's real tempting to say, well, we should have to calculate hours and so on and so on. And maybe we can. We definitely can. But the problem doesn't ask for it. So there's really no reason to do it. Okay? So as a result, we're not going to. All right? It makes our lives easier, and there's no reason to do anything. We can mark our units just fine, and everything will be nice and square. Okay? So let's do this. So 80 divided by 60 is 80 divided by 60 knock out those, and we have 8 over 6, or what is that? 4 over 3. 4 over 3 kilometers per minute. Or, you know, if you don't like fractions, 1 and 1.3 repeating kilometers per minute. How are we doing so far? We're doing pretty good. Anybody just a little bit nervous with the rain? I know that happens to me once in a while. Okay. All right. Oh, okay. Is that more clear than it was in the past? Okay. Well, excellent. Now, will the 5-minute apply for the position? Okay. Fair enough question, Philip. So, the 5 minutes means nothing at all. Means nothing at all. It is just there. Like, it means about as much as if we'd been telling you he was drinking Diet Dr. Pepper instead of regular Dr. Pepper while he was driving his car. It literally means nothing at all. I know that the thing that's really tripping you guys up is why would we give you information that doesn't matter? It's to sort of force you to think about what does and doesn't matter when it comes to the problems that we give you. That is legitimately the reality of it. We're told how long it takes to get to the end, so nothing else matters. Right? Because our equation right here is total distance divided by total time. So it does not matter. I mean, let's read through the problem again and see if in fact I'm making a mistake. Eustace drives 20 kilometers to the east when he realizes that he left his wallet at home. He drives 20 kilometers west, takes 5 minutes to find his wallet, and then leaves again. Now here is the important part. Eustace is 40 kilometers east of his house, exactly 60 minutes after he left the first time. Okay, now I apologize for the pedantic reading, but it means that the only thing that matters is the 60 minutes at the end. That's it. How are we doing? Okay, well, let's see. Let's find the velocity. So our velocity is equal to our, so average is equal to our total delta x over our total time. Now, what's our total time? What does the problem say our total time was? It says 60 minutes from the time he left the very first time. Okay, so in the problem it says that he is 40 kilometers east exactly 60 minutes after he left the first time. That 5 minutes that he spent looking for his wallet was after the first time he left his house. Okay, so that 60 minutes includes that 5 already. there is no adding to be done. It has already been done for us. Okay, but let's go ahead and continue on with this guy. So our delta x, same deal. We add up. The first one, let's call east positive. So to the right is positive. So 20. And then since he drives back, we take 20 off. So minus 20. And then he drives 40 to the east again. So plus 40. And so 20 minus 20. 20 minus 20 is 0. Plus 40 equals 40 kilometers, right? km. And then our total time is 60 minutes. Like, I really do understand why that feels weird. It's by design. We designed the problem that way. We designed the problem to make you uncomfortable. But I promise you, it doesn't matter. Because, like I said, that 5 minutes is in between the first time he left and where that 60 minutes runs out. Okay? And because of the way the problem is phrased, anything that happens between the first time he left and the 60 minutes at the end is included in that 60 minutes. Okay? How we doing, Philip? Let's continue doing our math. Okay. So, again, the first time he leaves his house is that 20 kilometers to the east before he comes back. So that 60 minutes includes the 5, because the very first time he leaves his house is that first 20. Then he turns around, drives 20, and waits 5 minutes before he leaves the house the second time. So that 60 minutes necessarily includes the whole thing. 60 minutes includes the 5. Do not add the 5. Don't do it. But so let's go ahead and finish calculating this. Okay, so we know our delta x, we know our delta t, we can plug these in. So our average velocity is delta x over delta t, or 40 divided by 60 km over minutes. And we still have our km and our minutes. So 40 over 60 is 2/3. Yeah, 2/3 km per minute. Bingo. There we go. Okay, so there we go. That is how we solve that problem from start to finish. Starting with a drawing, we just placed an origin. We drew that he drove from 20 to 20 here, and then from 20 back to 20. He waited 5 minutes here, but this 60 minutes over here at 40 includes everything from the very first time he left his house, so that 5 minutes does not matter. And there we go. Okay, so we have our 4/3 kilometers per minute because our distance just adds up everything divided by our total time, 4/3 kilometers per minute. And then same deal, but this time for the velocity we take into account the direction of each one of those displacements. Okay, so we go from 0 to 20, that's positive, then we go back from 20 to 0, so that takes it off. So now we're back down to 0, and then we go from 0 all the way back to 40 over the same 60 minutes. And instead we have 40 over 60 minutes, or 2/3 of the time. Okay? Excellent, excellent, excellent. Okay, everybody take a moment to take any screenshots or anything. I'm going to get just a sip of water and I'll be right back. Okay, we're doing good. Now let's go ahead and knock this off. All right, so let's go ahead and say I'm going to do number 7 next, and then I'll try to do number 9, and then I think that will take me to over an hour, and then I'll go ahead and call it quits. Okay? Are y'all enjoying this format? Like I said, I downloaded this this little overlay. Pretty soon I hope to have a a webcam that'll fill in that little black box up in the upper left-hand corner, because you guys are doing a great job engaging with this platform and helping me get over 5 average viewers. I really like that whole thing. I enjoy this a great deal, and I hope you guys are too. So let's go ahead and take a look at number 7. Where did I put it? Oh, I'm looking at the wrong one. Okay, number 7. You drive a car 2 hours. Okay, so can you do number 12? Oh yeah, sure. And that one's actually short. You know what? I can do both. Is anybody out there not followed? I would greatly appreciate it. But either way, if you're just forgetting, don't forget to hit that follow. Anyway, so let's do number 7. You drive a car at 2 hours at 40 kilometers per hour. Then 2 hours at 60 kilometers per hour. What is your average velocity? Then B, do you get the same answer if you drive a distance of 100 kilometers at each of the 2 speeds above? Okay, so let's go ahead and get started. Let's see if I dip off frame here. Okay, so let's go ahead and break this up into delta T1 and delta T2. Just there's 2 parts of this, so let's just deal with it that way. So 2 hours and 2 hours, and then V1 and V2 is, okay, so the first one is 40k per hour, and the second one is 60k per hour. Okay, now, okay, average velocity and 100 kilometers at each one. I may have to come back to that. Now, is there any reason to have to convert any of our units? We have hours and hours, hours and hours, and then we have 2 things in kilometers right there. So everything seems like it should work out real well, real straightforward, and nothing crazy, okay? So let's go ahead and see. It's asked for our average velocity. And now our average velocity, like we mentioned in the last problem, is V average equals delta x total over delta t total. Yeah? Delta t total, delta x total. So we have to find out our delta x total and our delta t total in order to find out our average velocity, okay? So let's do the easy one first. I like to start with the easy ones. Delta t total is just this one plus that one. So 2 plus 2 equals 4 hours. Okay? There we go. Next, our delta x total. Now that one's a little trickier, so we need to add up our delta x1 plus our delta x2. And I like to handle them in sections just in case I think it makes anything easier. So delta x1 is just equal to, well, okay, so let's put a pin in that exactly. Our equation that we're familiar with right now is V equals delta x over delta t, right? And we know our V and we know our t, so we can plug it in. Let me move over here. So for V1 equals delta x1 over delta t1, right? And so we have enough, we can plug that in. So 2 hours equals, oh, nope, I did it wrong. Start over. Call it an audible. All right, so V1 is our kilometers per hour. 40k per hour equals our delta x. We don't know that yet. That's what we're trying to find out, right? So delta x1 over our 2 hours. Okay. Now, however far we go, divided by 2 equals 40, right? So if we multiply both sides by 2, we end up with a delta x1 of 80 kilometers. Okay? Have I lost anybody yet? Okay. Good. Next, let's start with our V2. And again, the part we're looking for here is this delta x2 over delta t2. This guy right here is what we're looking for, okay? So let's go ahead and plug it in again, but this time it's 60k over hour equals our delta x, because we don't know that yet, divided by the same 2 hours. Multiply both sides by 2 to help cancel, I should have done that up here, help cancel out these Not directly, no. And actually, you know what? Because they're for the same amount of time, you could, but that only works if it's for the same amount of time. Okay? Because it's 2 hours and 2 hours, that does work, but only in this case. Okay, I'll show you in just a second. But either way, so multiply both sides by 2, and we have 120. Let's go ahead and stay consistent. Delta x2 equals 120 kilometers. Yeah, hold on just 1 second, Philip. I'll tell you what it means. All right. So now we can use this equation right here. Okay, we're just going to calculate our delta x total. Yeah, and we have 80 plus 120. So delta x total equals 80 plus 120 k, or 200 kilometers. And then our very last calculation for this part of it is our average velocity is equal to our total x over our total t. Right? And we've already figured out that it's 200 up here. And what did we say? 4 hours. 4 hours down here. We have our kilometers per hour, which is good because we're looking for a velocity. We end up with 50 km per hour. Okay? So I'm going to give you a chance to copy some of this work down, and then we'll move on to address Philip's question about whether or not we could add up the velocities, and then we'll move on to number 9. Okay, we are doing number 7. Oh, we'll finish up number 7, and then we'll do number 9 or number 12. Yeah, number 9 and number 12 are both easy. Hey, I like that emote. You know what? I actually did learn how to play Minecraft for education. It's a very powerful tool. It's just not particularly useful for physics education. We might use it a little bit for prototyping our roller coasters later on in the year, but we're not going to use it as much as I would if I were a chemistry teacher. But I am a physics teacher by choice. All right, everybody got this? So I'm going to go ahead and delete it. Or let's say delete everything up for, yeah, I'll delete most of it. Okay, so now what it's asking is what, oh, little praying doggy. Okay, cool, I like it. Looks like a Boston Terrier. Those are cool dogs. All right, so now in this one it says, okay. So can we just add up these two velocities, right? We have a 40 v1. So we have a v1 equals 40. v1 equals 40. And okay, so let's go ahead and write this down. We calculated a v average of 50 k per hour. And 40 k per hour. V2 is 60 k per hour. Okay, so boom, there we go. Starting off, we got our two things. Now, can we just add them and divide by 2? I mean, that is kind of a way that we do averages, right? So in this case, 40 plus 60 divided by 2 equals 100 divided by 2, or 50. You're right. This one time it worked. But don't do it this way unless they drive for the exact same amount of time. Okay, because the second part of this, the one where they both drive 100 kilometers, is going to show you that if they drive for different amounts of time, this will not be the same. Okay, so 40 plus 60 divided by 2 is 50. But I'm going to show you an example, just the second half of this number 7, where the average velocity will not be 50. Okay, so let's do it. Okay, so v1, v2, still 40, whatever. But now it says that if they both drive 100k at their speed, so delta x1 is 100 km, delta x2 is 100 km. Okay, And again, now we're trying to figure out what our average velocity is. And still, our average velocity is delta x total over delta t total. And let's go ahead and delete this too, because this will be different. Delta x total over delta t total. Okay. Now this time the easy one is our delta x total. It's just going to be 1 hundo plus 1 hundo equals 200 km. Yep. Super easy, real easy to knock out. Okay. But now we have to figure out our times. Okay, we need to figure out delta t1 and delta t2. Okay. But let's go ahead and start with our v equation. It's a simple place to start, and it always works. So v1 equals delta x1 over delta t1, right? And we know v and we know t, right? So we have 40 km over hour equals 100 km over delta t. Okay. Now we don't know that yet, but if you remember your algebra, you know you can just swap this and divide 100 by 40, or if you do 40 km per hour equals 100 km over delta t, you can multiply both sides by delta t and divide both sides by 40, and we end up with delta t equals 100 over 40, or 2.5 hours. Okay, so we have 2.5 hours. Yeah. Now we do the same thing, but with the second one, or 60 km per hour equals 100 over delta t, right? Because it's the same distance, same km. And same deal, we just swap these right here, and delta t equals 100 over 60, and we end up with 1 plus 40 over 60, or 1 2/3, or 1 2/3 hours. Okay? So, boom, there we go. Knocking this out. So now we know our two times, t1 and t2, and our total time is, 2.5 plus 1 2/3. So that one's harder to do in my head, so let's go ahead and do an approximation. Okay, 2.5 plus 1 plus 2 divided by 3. So 4 1/6. 1.6 repeating hours. Okay, so boom, there we go. Now we've got our total time. Okay, and now all we gotta do is plug it all in back at the beginning. So our velocity average is 200 km divided by the total 4.16 repeating hours, and again we have our kilometers per hour, and that gives us 200 divided by that, or 48 kilometers per hour. Okay, so and box it. I even said to box it today. All right, so now, like we mentioned before, if we just took 40 plus 60 divided by 2, we'd get 50. But as you can see, that's not always the case. And frankly, there's only one time that 40 plus 60 divided by 2 would give you the average velocity, and it's if they drive the exact same amount of time. Okay? Other than that, it's going to be something different. And so, like if they're driving the same distance, the slower one, okay, you keep asking for new ones before I'm done with the last one. Anyway, so the 40 kilometer per hour was driving for longer, so it was starting to pull the average down. So it's going to be a little closer to 40 than it was to 60, right? So There you go. I mean, it's sort of like if you have grades, the more low grades you have, the more it's going to drag those grades down. So just doing the straight numbers, like the longer we drive at 40, the closer our average will be to 40, right? And in this case, we drove at 40 for a lot longer. So that brought the average closer and closer to 40. So everybody take a look at this. I'm going to look at the next problem. And okay, so we're going to do number 12? Okay. Okay. I liked the little Minecraft guys. Okay, we got this one. Let's commit it to memory because it is time to move. Let's do number 9 and number 12 and we'll be done. I think number 9 is tougher than number 12. And both of those will be pretty quick. Okay, so number 9. A certain bacterium swims with a speed of 3.5 micrometers per second. How long would it take this bacterium to swim across the diameter of a Petri dish that is 8.4 centimeters wide? Okay. Now this one is most interesting for its dimensional analysis. Okay. So our velocity of our bacteria is 3.5 micrometers per second. That weird little UM thing is the Greek letter mu, and it's the lowercase version, and that's what we use for micrometers, okay? And so our total delta x is 8.5 centimeters, right? Let me make sure that that's right. 8.4. Okay, 8.4. Now, what that means is, because we have micrometers and centimeters, is we need to convert our centimeters into micrometers, right? And because centimeters are so much bigger, this 8.4 is going to be a lot bigger, okay? So, there are how many micrometers in a centimeter? Okay, so there are 1 million micrometers in a meter. 1 meter. Okay? And again, we're going to have to get rid of that centimeters there. So we're going to have to multiply it by something where centimeters is in the bottom. There are 1 million micrometers in a meter. There are 100 centimeters in 1 meter. Okay? So if we knock off 2 of those zeros, we can convert this number right here into centimeters by multiplying it by 10,000 micrometers per centimeter. Centimeters gets canceled out, and 8.4 times 10,000 is 84,000 micrometers. That's our total distance, and we already have our velocity. So now what we're left with is we can just use our standard equation. V equals delta x over time. We know our v, we know our delta x. Let's go ahead and plug it in. 3.5 equals 84,000 divided by delta t. And again, we can swap these and divide them, right? So we can divide 84,000 by 3.5. And we end up with delta t equals 84,000 divided by 3.5, or 84,000 divided by 3.5. There's my delete button. There we go. Okay. Or 24,000 seconds. I mean, it's kind of bonkers. Yeah. Okay, so 1 micrometer is times 10 to the negative 6th of a meter. Okay, so what that means is 1 meter over 10 to the 6th, right? A micrometer is very, very small, and times 10 to the 6th is 10 to the 6th is a million. So a micrometer is 1 million micrometers equals 1 meter, right? And a centimeter is 1/100th of a meter. Yeah, you're going to have, no, you don't convert it to meters. Well, you do kind of, but only because this way I can figure out exactly how many micrometers are in a centimeter. Okay, so I took my 1 million micrometers equals 1 meter, divided it by 100 centimeters equals 1 meter. These guys cancel out right there, and what we're left with is 1 million over 100. Yeah, but I like to do it by hand as best I can. The more I understand about the more different ways to do it, the better it is and the fewer wrong answers I get. But if you got the same answer, then boom, there you go. I mean, right answers are right answers. Your calculator is correct. This isn't like the last one where your right answer was only accurate in one particular place. This right answer would be accurate almost everywhere. Okay, so that's what we're doing. But there's your answer. So you got the right answer, Philip. Congratulations. Now let's see. Let's do one last one. Thank you for your questions. Thank you very, very much. And let's do it, number 12. If the average speed of an orbiting shuttle is 19,800 miles per hour, determine the time of orbit. Determine the time to orbit the Earth. The shuttle is orbiting about 200 miles above the Earth's surface, and the Earth's radius is 3,960 miles. Okay, so let's draw our surface of the Earth. And yes, absolutely, 100%, we are sure that it is curved. So right now we have a radius of 3963, right? Isn't that it? 3963? 3963 miles. But we are orbiting up here another 200. That is improperly drawn. That is another 200 miles above the Earth. Okay, so our actual radius from the center of the Earth all the way up here is, so our radius total is 4163 miles. Okay, so our actual path is way out here, and our circumference, the total length of our path all the way around one circle, is going to be, let's go ahead and call it our delta x. I know it's in a curve. The 200 miles does apply because this right here is where we're actually orbiting. Okay, so we're actually orbiting not at the surface of the Earth. We are orbiting 200 miles above it. And because it's a circle, it actually adds up very, very quickly. So it's not so small that we can neglect it. Okay, so we have to calculate our radius of 4163. And in this case, our delta x, the length of our path, is the circumference of a circle, or 2 pi times our r, or 2 pi 4163 miles. Doesn't just give the distance away from you? Or is that the displacement from the Earth? Okay, so our displacement is actually the length we travel in our circular orbit. Okay, so it's how far we go in that circle around the Earth. And like it says in the problem, the Earth itself, the actual from the center to the ground, is 3,963 miles. But from the center of the Earth to where we are is 3963 plus 200. So it's further away. And it affects how long that circle is that we're taking around the Earth. So let's calculate the length of our path. So 2 times pi times 4163 equals 26,156.9. 26,156.9 miles. Okay, 26,156.9 miles. Good. Now that's the length of our circle. That's how long the circle is that our little orbiter is flying around in. we are orbiting 200 miles above the surface of the Earth. Again, we have to calculate how long our circle is around the Earth. So that 200 absolutely applies in this case. Right? Because if we were just walking around on the surface of the Earth, if we walked a circle around the Earth on its surface, our radius would be that 3963. But we are actually 200 miles further out. And there's no reason to subtract the yeah, of course yes, it is 200 elevation beyond the surface of the Earth. And so if we have a circle like this is the radius of the Earth, right? Right? But we're actually orbiting around here. So the radius of our circle is all the way out here to that elevation. So if this right here is 200, then in order to figure out how long this circle is, we have to add this radius and that. I mean, at some point you just got to trust me. It is 100% that. But either way, here is our delta x, okay? And then, what does it say? We are moving at 19,800 miles per hour. So our velocity is 19,800 miles per hour, okay? And we have our regular equation for velocity. It's just velocity equals delta x over delta t. We're trying to solve for delta t. Now I know. I mean, feel free to prove me wrong. It's happened before, but not in this case. So we have 19,800, and we are traveling 156.9 miles. That's the length of how far we are going. And we're trying to figure out what the time is that it would take to cover that distance, right? Straight line or in a circle, it doesn't matter. All right, yeah, I'm not upset about it. I'm not upset about it, Philip. Don't worry about it. Anyway, so again, we're going to be able to take this, swap it here, swap that there, and we can just divide them. So we have our delta time is equal to 2615.6.9 divided by 19,800. Okay, wrong one. Or what that gives us is 1.321. And again, this is a time. This is a time, so we need a unit of time. So hours. There we go. Now let's see if I can't take one last hack at trying to explain why the 200 miles elevation matters to this whole thing. Everybody take a look at this, copy it down, and we'll talk one last little bit, and then I gotta bounce. Okay, so an orbiting body travels in a circle around a thing. Yeah? The length of that path is equal to, the delta x of that path is equal to 2 times pi r, or the radius of that object, right? Whatever it is that you're flying around, however far from the center of it you are, that's your radius, because that's going to tell you how far you are traveling in a circle around that object. In this problem, it's not a point in space that we're trying to fly around. It is an actual body. It is a big circle that itself has a radius of, like I said, 3963 miles. But we're not traveling just along its surface, right? We are actually traveling out here, another 200 miles above its surface. So the radius of the circle that we are traveling in, the radius of the track that we are riding around in, is actually 200 miles bigger. And as a result, that circle is much, much longer, right? So we can see from this that the radius of our circle, the radius of the circle we are actually traveling in, is 3963 plus the additional 200. Okay, so as a result, our path that we are traveling around in is actually 2 pi times 4163. Okay, so that's why that matters, is because the circle got bigger. Okay, and the reason it matters to our problem is because that 200 miles isn't just superfluous information about some other satellite. We are actually in the shuttle that is doing that traveling. Okay, that's why it matters to us. Okay. Well, thank you very much, everybody. If you're new to this, please remember to follow, or if you are one of my students, please follow on Twitter for updates for the classroom and I think a little bit of entertaining content regarding the rest of this channel. I bet all of you are going to do pretty good in the test and the quiz tomorrow. Take use of the peer tutoring, and I will talk to you guys tomorrow. Thank you.